So this is the second half of 13.3. So last time we gave a definition of a partial derivative. We talked about the geometric interpretation of partial derivatives, and we practiced on visualizing what our partial derivatives tell us. We calculated a few. Today we're going to talk about second partial derivatives, third partial derivatives, etc. Just like we did for functions of a single variable. But if because we have more than one variable, so we'll just start with two variables. If z is a function of x and y, then we have four possibilities for a second partial derivative. And we call them second partials just as kind of a shorthand. Our first derivative, we can take the derivative with respect to x of the first partial with respect to x. We can also write that as fxx. That's the same as the partial with respect to x of the first partial. And we write this as d squared f dx squared. So we take the partial with respect to x and then differentiate that function with respect to x again. Our second possibility, we can take the partial with respect to y of that first partial with respect to x. We write that as f sub xy. That's the same as the partial d dy of df dx. And note the difference in order of the notation here. We write this as d squared f dy dx. So when we use the subscript notation, our order of integration is left to right. When we use the d notation, our order of integration is from right to left. Our third possibility, we first take the partial with respect to y of our function and then differentiate that with respect to x. We write that as fyx. That's d dx of df dy. And we write that as d squared f dx dy. And our final possibility is we take our partial with respect to y both times. And that's fyy, or d dy of df dy, and that's d squared f dy squared. So it's important to remember that with our subscript notation, our mixed partials, we call these two partials the mixed partials. The order of differentiation is left to right. When we use the d notation, the order of differentiation is right to left. And again, the number 2 and number 3, these two possibilities, we call them the mixed partials, or the second mixed partials, because we're doing the differentiation with a different variable on each step. One nice thing about the mixed partials is that in advanced calculus, we're not going to do it here, but we can prove that if these mixed partials are continuous, then they're equal. So our second, in general, we're going to be working with nice functions where our second mixed partials are going to be continuous. So in general, we can say that the mixed partials are equal. And what will make that just a little more formal. So we're going to say that for f of xy, such that our mixed partials, f sub xy and f sub yx, are continuous on an open disk. We'll call our open disk R. Not open disk R, open disk of radius R. Then our mixed partials, f sub xy equals f sub yx for every point in R. So this is just a fancier way of saying that if our functions are continuous, if our second partials are continuous, then they are equal. And this holds for functions of higher number of variables as well. So if we have a function of 3 variables, if the second order partials are continuous, then the third mixed partials are equal. If we have a function of 4 variables, if the third mixed partials are continuous, then the fourth mixed partials are equal. So in general, if we're working with a nice function, our mixed partials are going to be equal. It doesn't matter which order we do the differentiation in, those mixed partials are going to be equal. So let's do a couple of examples calculating some mixed partials. Anybody have questions before we move on? Okay. So we'll just do some examples. This is pretty straightforward. Just want to get some practice working with these. So we have z equals x to the fourth minus 3x squared y squared plus y to the fourth. We want to find the 4 second partials. So let's find our first partials first. So dz dx, what's dz dx going to be? 6x y squared. And that's it, because y is constant. How about dz dy? What is it? Dz dy? We're just doing the first partials here. Minus 6 x squared y plus 4y cubed. So there's our first derivatives. Now let's look at the derivative with respect to x of dz dx. So what do we get? 12x squared minus 6y squared. Let's look at dy of dz dx. What do we get? minus 12xy. Let's look at d dx, make a nicer d there, of dz dy. We get minus 12xy again. And we see that for this particular function, our second mixed partials are equal. And how about d dy of dz dy? Minus so there are our four second partials. And we can see that our mixed partials are equal. Let's see. Let's look at, I just want to look at some true or false questions, and then and that's all I want to talk about today. So in your book, on page 914, there are some true or false questions I want to talk about. You guys need to borrow a book?
Yeah. Oh, yeah. Thank you. I considered bringing my book. I looked at it, and I was like, no. Is it hour long today? I don't know. Is it hour long today?
No, I don't. There aren't any more hour-long freshman seminars.
Oh. You guys get bad news.
Because it's not really freshman seminar anymore, unless we do an hour when we have to pick classes. I'm not sure, but because it's a different thing, second semester. All right, so we're looking at page 914, number 95. Page 914, number 95.
We're supposed to film. I can't do it.
Think about it.
So this one isn't true or false. It says N is the number of applicants to a university. P is the charge for food and housing, and T is tuition. So N is a function of P and T. And we know that it tells us that the partial of N with respect to P is less than 0, is negative, and the partial of N with respect to T is less than 0, so that's negative 2. So what do those pieces of information tell us? So if if we're taking the derivative, if the derivative of the number of applicants with respect to the cost of the food and housing is negative, what does that tell us?
Does that mean that the higher the cost for food or housing goes, and tuition, the lower the number of applicants apply?
Okay, so Caitlin says as the tuition cost goes up, as food cost goes up, that we have less applicants. So that's exactly what that tells us. All right, now let's look at number 915, number 103 through 106. These are true or false. So we want to answer true or false or provide an explanation.
Okay.
So page 915, number 103 through 106. The first one says if z is a function of x and y, and the partial of z with respect to x equals a partial of z with respect to y, then z is in the form some constant times x plus y. Is that true or false? And provide an explanation.
Well, you could have some squares in there, as long as they're both the same power.
Well, I think it's false.
Wait, Scott. It's college.
It's false.
So Caitlin says false. Why, Caitlin?
Because there are different functions that z can be to where there's first partial derivatives.
Okay, so Caitlin says there are different kinds of functions, and Scott came up with an example. You could just have a +1 at the end. X plus y plus 1, and that would work. The partial with respect to x would equal the partial with respect to y. So that's one example. All right. Number 104. If z is f of x times g of y, then dz dx plus dz dy is f prime g plus f g prime. I'm going to write that one up.
True. Why is it true?
No, it's not me. They stopped using that.
This is why I want to come to class tomorrow. Is what we're learning tomorrow going to be on the quiz on Thursday?
There will be one question, I think, on what.
What is that over there? They're like pyramids and stuff.
But yeah, those are polyhedrons.
Can we see them?
When we're done talking about this, yes.
I say true.
I say. Nose goes. I don't know. Caitlin and say true.
Yeah. Oh, wait.
All right, so here's our question. All right, guys, listen up. So here's our question. If we have a function in the form f of x times g of y, then the partial with respect to z, the partial of z with respect to x plus the partial of z with respect to y looks like this. True or false?
False.
Well, let's
True. I say true.
let's calculate it. dz dx. All right, guys, listen up. The partial of z with respect to x, let's calculate that. What do we get? F prime of x times g of y. G is just a function of y, so this is just a constant. dz dy is what? F of x, because that's just a constant, times g prime of y. And if we add these two together, we get this. So that one is true. All right.
True.
The next one, if z equals e to the xy, then the mixed partial of z is x plus y, xy plus 1 times e to the xy. So basically it's asking you to calculate that mixed partial and see if that's true. So calculate that and see if it's true.
False. As far as I'm getting.
So we have one false, we have one true. Any speculation from the back row there? You guys that are working on these mixed partials really hard? Scott says false.
Scotty agrees with you.
All right, so let's look at this one. Which derivative is this telling us to take first?
dy. I mean dx.
We have to take the partial with respect to x. So let's do dz dx equals what? Y e to the xy. Does everybody agree? And then we want to take the partial with respect to y of this. So we're going to take dy of y e to the x y. So what, and then we get, what do we get for this? E to the xy plus xy e to the xy, and this simplifies to this. So this is true. All right, last one.
Is it 106?
Number 106, yes. If a cylindrical surface has rulings parallel to the y-axis, and let's remember, rulings means that the rulings connect the generating curves. So if we have our generating curve as a parabola, and our rulings are parallel to the y-axis, so that would mean we'd have a parabola, a parabolic cylinder along the y-axis, and our rulings would connect those parabolas along the y-axis. So if our cylindrical surface has rulings parallel to the y-axis, then dz dy is 0.
False. Wait.
So the example I gave was a surface. I'll just sketch it up here really fast. So if we had a cylinder
False.
like so, and my rulings were parallel to the y-axis, so I'm going to connect my cylinders here along the y-axis. So my rulings are these dotted lines. So my surface is that parabolic shaped trough. Is the partial derivative of this surface with respect to y 0?
False, because couldn't y be, like, it could be any constant, and then it could be, like, the function could be yx squared, so then,
Yx squared wouldn't be a cylindrical surface.
right.
So if we're thinking about this particular surface, if we're moving in the positive y direction, are we going uphill or downhill? Neither. So our derivative, our partial with respect to y would be 0. So that would be true. All right. Any questions? Second, higher order partials, pretty straightforward. What we're doing with these partial derivatives now is we're like we did with our vectors, we're building a foundation. On Thursday is when we start getting into the really interesting stuff that involves our partial derivatives. We're going to start talking about the gradient, and that gives us some really nice.
Application problems?
What's that?
Is it application problems?
Gradients, gradient has some applications, but the gradient is interesting all by itself too. All right, homework. Homework, page.
Yes. Yeah.
She just has the for the essays. There's nothing for
Me.
She emailed us, and she's just like pretty much, hey, you're not gonna get this test today, and you're doing it. I wanted to win the email.
That's what I got from it.
no, the stuff on the website is just for the written.
I like the team.
But there's nothing that has the quotes all over the place. No. So how are we supposed to study?
You guys don't, it says that there's stuff because they about this. No, they're gonna.
She said there's gonna be like short answers on
They
these.
need one.
Did you see?
All right, there you go.